Okay, in this section we're going to look at the laws of exponents, and we're going to try and go through them one at a time and see why each one is true. So just to start off, what I'm going to look at is what happens if I multiply two different exponents together. So here's what I mean. So what if we had something like 2 to the 5th times 2 to the 3rd? What happens if we multiply those two together? Let's try it out. So 2 to the 5th means 2 multiplied by itself 5 times. So 2 to the 5th I could rewrite as 2 times 2 times 2 times 2 times 2. 2 cubed I could rewrite as 2 times itself 3 times. Which would give me this. Notice there's a little bit of weirdness with parentheses, but if you check the meaning of this expression versus this expression, our order of operations says you do the exponents first, so 2 to the 5th first, and 2 cubed first, before you deal with multiplying anything together. So that should have the same meaning as what I have written here, 2 to the 5th power in parentheses, and 2 to the 3rd power in parentheses. But now that I have it written this way, we have our two rules, associative and commutative rules, that say if you're multiplying a bunch of 2's together, it doesn't matter how you do it. Either left to right, grouping in different ways, you should always get the same answer, as long as it's all multiplication, 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 which this is. And if you'll notice, how many 2's do we have? 1, 2, 3, 4, 5 from 2 to the 5th, 1, 2, 3 from 2 cubed. So we have a total of 8 2's multiplied together. And so this should give me the same answer as 2 to the 8th power. And so I'm going to take a step back and try and see, where did this 8 come from? Was there anything magical about this 8? No, not really. There were 5 2's, there were 3 more 2's. We added those up. We got a total of 8 2's. We had 5 and 3 is 8 total. So really this exponent came from adding up the two exponents. So it's really 2 to the power 5 plus 3. And so that's going to be our first law of exponents, is if we multiply two numbers with the same base, what we're going to end up doing is keeping that base, and we're going to add their powers. So this is a little bit more complicated way to write than this, but this is equivalent to the original. So our first rule that we're going to write down is if we have an exponent times another exponent with the same base, we're going to add their powers. In this case, 2 to the 8th power would be some other number. Let's see, that'd be 256, I believe. I don't really care about that. Okay, well, let's try another example. Let's look at a quotient. What if I had 3 to the 7th power divided by 3 squared? And suppose I wanted to try and figure out what that's going to be. I'm going to use the same strategy, rewriting each exponent as a product of a bunch of numbers. So 3 to the 7th would be 3 times itself 7 times. One, two, three, four, five, six, 7 3's. 3 squared would be 3 times 3. And then hopefully you guys remember how fractions work. If everything in the numerator is multiplied and everything in the denominator is multiplied, then what we can do is cancel any factors we see in common. So they both have a 3 in common. I can cancel that out. They both have another 3 in common. I can cancel that out. And what I'm left with is this. 3 times 3 times 3 times 3 times 3 in the numerator, which we talked about this in the last section. 12 is the same as 12 over 1, and so 3 times 3 times 3 times 3 times 3 over nothing, or over 1, would be the same as just being in the numerator. Which is equal to, let's see, 9 times 3 would be 27, times 3 would be 81, times 3, I believe, is 243. That's irrelevant. Why did I even bother to write that down? That doesn't help us at all. We're trying to come up with a rule of exponents. So let's see, if we have 3 to the 7th on top and 3 squared on bottom, what we ended up with was a power of 3. Which power of 3 is it? Well, there's 5 3's, 3 to the 5th. And let's see, how is this related to these original numbers? Well, we started with 7 3's in the numerator and 2 in the denominator. 2 is how many we were able to cancel, so we take the exponent in the numerator, and we're able to cancel this many, so we're going down this many. So I guess the rule, the way we come up with 5 from 7 and 2 is we subtract them. And so there's our second rule of exponents. Apparently, if we have a fraction where we have an exponent over an exponent with the same base, what we're going to do is subtract those exponents. Okay, the book calls these the product rule and the quotient rule. I don't know that I care enough about that to call them by a specific name. The nice thing, though, is if you, like me, have an utterly terrible memory, it's okay, because we can sometimes figure out what these rules are supposed to be by plugging in simple numbers like these 3's and 5's and 7's or 2's and 3's. Plug in some simple numbers and check, is the left side that you think you have equal to the right side? If yes, then you probably wrote down the rule correctly.